At 4 Aumentoirt in the morning, a fighter pilot can be flying hundreds of miles from the Iranian border and already be part of an engagement that the opposing pilot may not even know has begun. Not a dogfight. Not two aircraft circling each other at visual range. A detection, targeting, and weapons chain designed to decide the outcome before the other aircraft gets close enough to fight on equal terms. And the weapon sitting at the center of that change is the AIM-260 Joint Advanced Tactical Missile, paired with something even more important than the missile itself. America's expanding network of stealth aircraft, fused sensors, electronic warfare, airborne surveillance, and long-range targeting. That combination could fundamentally change the air-to-air equation facing Iran. I'm going to walk you through exactly how that system works, why range alone is not actually the most important advantage here, and why the widening gap between America's air combat architecture and Iran's fighter force could matter far more than simply comparing how many aircraft each side can put into the sky. Because this is not really a story about one missile. It is a story about who sees first, who understands first, who shoots first, and who survives long enough to shoot back. Stay with me for all of it. Before we go further, one distinction matters. Military technology is surrounded by classified information, incomplete reporting, manufacturer claims, intelligence assessments, and speculation. Some characteristics of the AIM-260 remain classified, including important performance parameters. Where information is publicly confirmed, I'll treat it as confirmed. Where credible reporting provides an assessment, I'll identify it as such. And where we're analyzing what these capabilities could mean in a hypothetical confrontation, that's analysis rather than a claim about a predetermined outcome. No hype, no speculation dressed up as fact. And there is another reason for that caution. Calling an air force obsolete makes for a powerful headline, but real warfare is more complicated. An older aircraft can still launch a dangerous missile. A ground-based radar can still detect something unexpected. A pilot can make the right decision at the right moment. A sophisticated aircraft can suffer mechanical failure, encounter an unforeseen threat, or simply be in the wrong place at the wrong time. Technology changes probabilities. It does not abolish uncertainty. So when we ask whether a new generation of American air combat weapons could make Iran's fighter force effectively obsolete in a high-end confrontation, what we're really asking is whether Iran can consistently complete the sequence required to fight back. Can it detect the attacker? Can it identify the attacker? Can it build a reliable firing solution? Can it transmit that information quickly enough? Can its fighters survive long enough to reach launch position? Can their missiles reach the target under realistic conditions? And can all of those things happen before the American side completes the same chain? That is the real contest. Let's get into it. Modern air combat is often explained as if it were a comparison between airplanes. F-35 versus MiG-29. F-15 versus F-14. Speed versus speed. Radar versus radar. Missile versus missile. That is increasingly the wrong way to understand it. An aircraft is no longer simply an aircraft. It is one node inside a much larger combat system. And once you understand that, the significance of a weapon such as the AIM-260 begins to look very different. For decades, the basic logic of beyond visual range air combat has been relatively straightforward. A fighter searches for an enemy aircraft using radar or information provided by another sensor. The crew establishes a track. The pilot gets into a position where a missile can reach the target. The missile is launched. Depending on the weapon, the launching aircraft may continue providing information during part of the missile's flight. Eventually, the missile's own seeker attempts to acquire the target and complete the interception. Every step consumes something: time, distance, energy, information. And every one of those things creates an opportunity for the opponent. If your radar has to transmit strongly to locate me, I may detect those emissions. If you have to fly toward me to get your missile into range, you are reducing the distance between us. If your missile has limited energy at long range, I may be able to turn away and force it to expend that energy. If your targeting picture is incomplete, you may not know which contact represents the greatest threat. This is why the longest advertised missile range does not automatically determine who wins. The engagement is a chain, and the chain begins long before launch. Imagine two fighters approaching each other. One pilot has a powerful radar but must use it aggressively to search. The other aircraft has a reduced radar signature and is receiving information from multiple sensors. The first pilot is searching for a difficult target. The second pilot may already be looking at a track generated from information gathered elsewhere. Those are not equivalent situations. One side is hunting. The other may already have found what it needs. The difference is where fifth-generation aircraft change the equation. The F-35's importance is often reduced to one word: stealth. But stealth is only one layer. The more consequential capability is what happens when low observability is combined with sensor fusion. The aircraft collects information from multiple onboard systems, processes those inputs, and presents the pilot with a consolidated picture rather than forcing the pilot to mentally assemble every piece of information independently. That matters because combat is not an engineering specification contest. It is a decision-making contest. The pilot who understands the battle space first has more options. The pilot who understands it second is reacting, and reaction consumes time. Consider what happens when an Iranian fighter is trying to defend a piece of airspace. Its mission may require it to protect a base, a city, a nuclear facility, a missile complex, or a command center. That requirement already limits its freedom. An attacking aircraft can choose its route. The defender frequently cannot choose what must be defended. That creates the first asymmetry. Then comes detection. A conventional fighter searching with radar is emitting electromagnetic energy. Modern warning systems are designed to detect and characterize emissions. So the radar that helps one aircraft see can also contribute information about where that aircraft is. Now introduce a stealth aircraft. Low observability does not mean invisibility. That distinction is essential. Stealth is not magic. It is signature management. The objective is to reduce detection ranges, complicate tracking, disrupt weapons quality targeting, and force an adversary's sensors to work harder. The difference can be decisive because detecting that something may be present is not the same as producing the precise, continuously updated track required to guide a weapon against it. This is one of the most misunderstood parts of the entire debate. A radar may detect an anomaly. That does not necessarily mean a missile battery or fighter has a usable firing solution. Search, detection, identification, tracking, targeting, engagement, those are different stages, and a sophisticated air campaign is designed to attack the connections between them. Now add electronic warfare. An enemy radar is no longer merely trying to detect a low observable aircraft. It may be operating while communications are being disrupted, decoys are appearing, electronic support systems are locating emitters, standoff weapons are threatening fixed sites, and other aircraft are forcing operators to divide their attention. The problem becomes cumulative. This is where the word cascading becomes useful. A radar site loses confidence in its picture. That reduces the quality of information sent to command centers. Command centers become slower at assigning targets. Fighters receive less reliable intercept instructions. Those fighters then have to depend more heavily on their own sensors. Using those sensors can reveal more information about their position. That gives the opposing force additional opportunities to track them. One weakness feeds the next. And suddenly, what looked like a contest between two fighter aircraft has become a contest between two information systems. That is the recontextualizing surprise. The AIM-260 is important partly because of what it can do, but its larger significance comes from what can tell it where to go. The missile was conceived as a successor to the AIM-120 AMRAAM family, which has been one of the Central American beyond visual range air-to-air weapons for decades. AMRAAM itself transformed aerial warfare. Its active radar seeker reduced the degree to which a launching fighter had to remain tied to the target throughout the entire engagement. Later variants increased capability substantially, but military technology does not stand still. Potential adversaries developed longer-range air-to-air weapons. Aircraft sensors improved. Electronic warfare became more sophisticated. And the United States needed a weapon designed for a battle space in which the launch aircraft might need to engage a sophisticated target from significantly greater standoff distances. Enter the AIM-260. Many of its exact capabilities remain classified. That is important. Public discussions frequently attach specific maximum ranges to modern missiles as though those numbers were fixed and universally meaningful. They are not. Missile range depends on altitude, launch speed, target altitude, target direction, maneuvering, atmospheric conditions, guidance profile, and how much energy the weapon must preserve for the final interception. A missile fired high and fast against an approaching target may have dramatically different effective reach than the same missile fired low against an aircraft running away. So the relevant question is not simply, how many miles can it fly? The better question is this: how large a region can the opposing aircraft enter before it becomes vulnerable to a credible shot? That region is sometimes described conceptually as an engagement envelope. Expand that envelope and you change behavior. An enemy fighter may have to turn earlier. It may have to stay farther away. It may be forced lower. It may have to use its radar differently. It may need support from other aircraft. It may be unable to reach the location from which its own weapon would be most effective. This is why a missile does not need to physically destroy an aircraft to influence the battle. It can control geometry, and geometry controls options. Suppose an Iranian fighter wants to approach an American formation closely enough to launch its best available air-to-air weapon. That fighter must survive the journey into its own effective firing envelope. If the American formation can threaten it before it reaches that point, the Iranian pilot faces a brutal decision. Continue forward and risk being engaged. Turn defensively and surrender the attack. Descend and potentially lose sensor or missile performance. Climb and potentially become easier to detect. Use electronic countermeasures and potentially reveal additional information. Call for support that may itself become vulnerable. Every choice carries a cost. The missile creates the dilemma. The network makes the dilemma appear earlier. Now, let's talk about Iran's side of this equation. Iran's military aviation history is unusual because parts of its fighter inventory originated in the United States itself. Before the 1979 Islamic Revolution, Iran was one of Washington's closest regional security partners. The Shah acquired advanced American equipment, including the F-14 Tomcat. At the time, the F-14 was extraordinary. Its radar and long-range missile combination was designed around a demanding mission: detect and intercept threats at substantial distances. Iran became the only foreign operator of the Tomcat. Then, the revolution happened. The strategic relationship collapsed, the supply chain was severed, and Iran spent decades keeping aircraft operational under sanctions, limited access to original components, and enormous logistical pressure. That achievement should not simply be dismissed. Keeping old combat aircraft operational without normal manufacturer support requires ingenuity, but maintenance ingenuity cannot freeze technology in time. Airframes age, engines age, wiring ages, radar architectures age, weapons age, and perhaps most importantly, the entire information environment surrounding those platforms changes. Iran later acquired other aircraft, including Soviet and Russian types, such as the MiG-29 and Su-24, while developing domestic upgrades and attempting to modernize portions of its aviation sector. But the challenge remained structural. A fighter force does not modernize merely because one new radar is installed or one new missile becomes available. Pilot training matters, flight hours matter, maintenance readiness matters, data links matter, electronic warfare matters, airborne early warning matters, weapons integration matters, command and control matters, secure communications matter, and all of those pieces must function together under attack. That is the gap. America's advantage is not that every American aircraft is newer than every Iranian aircraft. It is that the United States has spent decades attempting to connect sensors, shooters, command platforms, satellites, surveillance aircraft, fighters, ships, and ground systems into a shared combat architecture. The result is imperfect. Networks fail. Data links can be jammed. Sensors disagree. Communications can be disrupted. Software introduces its own vulnerabilities. But the direction of travel is unmistakable. The individual fighter is becoming less dependent on what its own radar can see. That has enormous implications, because if a fighter can receive a high-quality target track without using its own radar aggressively, the opponent may have fewer indications that an engagement is developing. And if a long-range missile can exploit that targeting picture, then the traditional warning sequence begins to compress. You may not see the shooter. You may not detect the shooter searching. You may not know which platform generated the track. And by the time your warning systems indicate that a missile is part of the equation, the most important decisions may already have been made. That is not science fiction. It is the direction modern air warfare has been moving for years. And critically, the weapon itself is only the final physical expression of the information advantage. Think of it as 3 layers. The first layer finds, the second layer decides, the third layer kills. Sensors find, networks and crews decide, weapons engage. Break any layer and the system becomes less effective. Strengthen all 3 and the effect compounds? Iran faces the opposite challenge. Its fighter force needs enough warning to get airborne. It needs enough information to position those fighters correctly. Those fighters need enough situational awareness to locate the threat. They need to survive enemy suppression efforts. They need to reach an effective firing position. And they need to do all of that against an opponent specifically designed to interfere with each step. That is why counting aircraft can be misleading. A country can theoretically possess dozens of fighters. But how many can launch at once? How many have fully mission-capable radars? How many have serviceable missiles? How many pilots are current for complex beyond visual range combat? How many can communicate securely when networks are under electronic attack? How many can be refueled, rearmed, and launched again after their base has been attacked? Those questions determine usable combat power. The number painted on an inventory spreadsheet does not. Now we arrive at the sequence that would matter in an actual confrontation. The first phase would begin before fighters started shooting at each other. Intelligence preparation. American and Allied forces would attempt to build a picture of Iranian air bases, radar coverage, command nodes, fighter locations, surface-to-air missile batteries, communications infrastructure, and known patterns of activity. Iran would be doing the same. Satellites would matter. Signals intelligence would matter. Airborne sensors would matter. Cybersecurity would matter. Human intelligence could matter. And deception would matter enormously. Neither side would want the other to know exactly where its most valuable systems were located. Then comes the first operational move. If Iranian commanders believe an attack is imminent, they face a dilemma before the first weapon is launched. Keep fighters concentrated at established air bases, and they are easier to maintain, arm, and coordinate. Disperse them, and they become harder to destroy on the ground. But logistics become more difficult. Fuel must move. Weapons must move. Maintenance crews must move. Communications must follow. Every dispersal decision trades efficiency for survivability. The United States faces its own version of the problem. Tankers, command aircraft, surveillance platforms, and large support aircraft are enormously valuable but are not stealth fighters. They must operate at safer distances. That creates an invisible architecture behind the visible strike package. Fighters at the front, support assets behind them, bases and logistics farther back, space and communications networks above all of it. This is why there is no invulnerable side. Every system has dependencies, but the dependencies are not equally exposed. Now imagine the first Iranian fighter launch. A warning arrives. Pilots scramble. Engines start. Aircraft taxi. The fighters climb. At that moment, they are not entering an empty sky. They are entering an information environment. Their departure may be detected by satellites, airborne radar, electronic intelligence systems, other fighters, or some combination of sensors. No single detection method needs to be perfect. The network's value comes from correlation. One sensor sees something uncertain. Another sees a second piece. A third adds identification. The picture becomes clearer. This is sensor fusion at the operational level. And once a track becomes sufficiently reliable, commanders can begin positioning shooters. Here's the piece almost nobody is explaining correctly. The F-35 does not necessarily need to charge directly toward an Iranian fighter with its radar blasting at maximum power. That is the old mental model. A modern engagement can involve information flowing among multiple platforms. The aircraft with the best view does not always need to be the aircraft that fires. The aircraft that fires does not always need to be the aircraft closest to the target. And the target may not know which node in the network is most dangerous. That ambiguity creates tactical pressure. Now the Iranian pilot has another problem. What exactly should he react to? A radar emission? A distant aircraft? A warning from a ground controller? An electronic attack? A possible missile launch? A target that appears briefly and disappears? Every reaction changes the geometry. Turn toward one threat and another angle opens. Turn away and you surrender distance. Descend to exploit terrain and you may reduce your own radar horizon. Climb to improve radar and missile performance and you expose yourself to additional sensors. This is the tyranny of modern air combat. There may be no perfect choice, only less dangerous ones. Then the long-range weapon enters. The American fighter reaches a firing solution. The missile separates. For the first few seconds, the Iranian pilot may know nothing has happened. That period matters. A missile is fastest and most energetic early in flight. The target's best defense is often not a dramatic last-second maneuver. It is denying the missile favorable geometry as early as possible. But you can only react early if you know the engagement exists. This is where stealth, passive sensing, networked targeting, and long-range weapons reinforce one another. Stealth delays detection. Sensor fusion improves understanding. Networking allows information to move. Range permits earlier engagement. The missile forces reaction. The reaction creates new information. The system feeds itself. That is the mechanism. Not one miracle weapon. A chain. Now consider three possible Iranian responses. First, the fighter continues toward the threat. That may preserve its offensive opportunity, but it also reduces distance to the incoming weapon. Second, it turns away. That improves survival probability against some missile trajectories by forcing the weapon to chase, but the Iranian fighter has now abandoned its intercept. Third, it maneuvers aggressively while using electronic countermeasures. That may complicate the missile's terminal solution, but maneuvering costs energy and can leave the fighter poorly positioned afterward. All three options may be rational. None is free. And this is why obsolete needs a precise definition. It does not mean the Iranian aircraft suddenly cannot fly. It does not mean its missiles stop working. It does not mean its pilots become incapable. It means the aircraft may struggle to perform its intended combat function against an opponent that can repeatedly impose unfavorable engagement geometry. That is a very different claim, and it is far more important. Because air superiority is not achieved by proving that every enemy aircraft is technologically inferior. It is achieved by preventing those aircraft from meaningfully interfering with your operations. If Iranian fighters are repeatedly forced defensive before they can threaten American strike aircraft, then the operational effect begins to resemble obsolescence, even if many of those fighters survive. The airplanes still exist. Their freedom of action does not. Critically, this effect becomes stronger as pressure spreads to the bases supporting them. A fighter needs fuel. A fighter needs weapons. A fighter needs maintenance. A fighter needs runways. A fighter needs trained ground crews. A fighter needs communications. A fighter needs intelligence. Destroying the fighter is only one way to remove it from the battle. Damage the runway, and it may not launch. Destroy fuel infrastructure and sortie generation falls. Disrupt command networks and the fighter launches without a clear picture. Threaten maintenance facilities and readiness degrades over time. Strike weapon storage sites, and the aircraft becomes increasingly limited. This is why modern air campaigns attack systems, not just platforms. Within the opening phase of a high-intensity confrontation, these pressures can compound rapidly. The first sorties challenge radar coverage. Follow-on strikes attack identified defenses. Electronic warfare complicates communications. Long-range weapons pressure air bases. Fighters attempt to intercept. Those fighters reveal patterns. Patterns generate new targeting information. The cycle repeats. Each loop can make the next loop easier, but there is a danger in assuming that this process is automatic. It is not. Iran is not defenseless. Its geography alone creates complications. The country is enormous. Mountain ranges break radar line of sight. Aircraft can exploit terrain. Mobile systems can relocate. Decoys can consume expensive weapons. Commanders can deliberately keep systems silent until favorable moments. Iran has spent decades preparing for conflict against technologically superior opponents. That preparation matters. An air defense system does not need to dominate the entire sky to be useful. It can survive. Wait, force caution. Create uncertainty. Protect one important location for one important hour. That may be enough to affect an operation, and the same applies to fighters. An older fighter positioned correctly can still be dangerous. A missile fired unexpectedly is still a missile. This is not a video game in which one side unlocks a superior technology and every previous unit disappears. War is full of exceptions. But strategy is built around probabilities. And the probability problem becomes severe when one side is simultaneously behind in signature management, sensing, networking, weapons reach, support infrastructure, and fleet modernization. The AIM-260 potentially adds pressure to the one area where Iran can least afford another disadvantage: distance. For years, one defensive answer to a superior fighter has been to remain outside its most dangerous engagement envelope. A longer-range missile pushes that boundary outward. Now the defender must remain farther away. That means the defended area becomes harder to reach. If you have to stand farther from the aircraft you're trying to intercept, then protecting a fixed point becomes more difficult. This is geometry again. And geometry does not care about propaganda. Let's put it into a simple hypothetical. An Iranian fighter is defending a strategic facility. An American strike formation is approaching. The Iranian pilot's objective is not necessarily to shoot down an F-35. His immediate objective may simply be to force the strike aircraft to change course or abandon the attack. But to do that, he needs to present a credible threat. To present that threat, he needs to get close enough that American pilots believe his weapons can reach them. If American fighters can engage him before he reaches that position, his mission becomes dramatically harder. He may survive, but the facility he was defending may still be struck. Tactically, he survived. Operationally, he failed. That distinction is everything. Now scale that from one aircraft to an entire theater. Iran has to defend multiple directions: the Persian Gulf, western approaches, northern airspace, critical infrastructure inland, military bases, nuclear-related facilities, missile sites, command centers, population centers. No fighter force can be everywhere simultaneously. The defender has to prioritize. The attacker can exploit that prioritization, pressure one sector, force fighters to reposition, threaten another sector, make tankers and support assets move, force radars to activate, collect information, attack the newly revealed architecture. This is why information superiority can become self-reinforcing. Every defensive reaction can create another clue, and every clue can improve the next attack. If this breakdown is giving you a clearer picture of how modern air combat actually works beyond the aircraft versus aircraft comparisons you normally see, do one thing right now: hit subscribe and ring the notification bell. Because the weapons, deployments, and operational lessons surrounding this story are changing quickly, and we're going to keep separating what these systems can genuinely do from what the headlines claim they can do. Now let's zoom out to what this means. The first ripple effect is local. Iranian fighter operations become more difficult, not impossible, more difficult. Pilots may be forced to remain closer to protected areas. Commanders may become more reluctant to expose scarce aircraft. Patrol patterns may become less aggressive. Radar use may become more cautious. The force begins behaving around the threat. That is the first sign that a weapon is exerting strategic influence. The enemy changes behavior before you fire it. The second effect is national. If fighters cannot reliably contest hostile aircraft at distance, Iran becomes more dependent on ground-based air defenses. That shifts pressure onto surface-to-air missile networks. Those networks now have to carry more of the burden. And the more heavily they are used, the more important their radars, communications links, and launchers become. That makes them priority targets. So a weakness in the fighter force increases pressure on the air defense force. If air defenses then become degraded, fighters lose another layer of protection. The cascade continues. The third effect is regional. Neighboring governments watch these engagements very closely. Saudi Arabia watches, the United Arab Emirates watches, Turkey watches, Israel watches, Gulf militaries watch. And they are not simply asking who won a particular engagement. They are asking what capabilities they need to buy for the next 20 years. If stealth aircraft paired with networked sensors and increasingly long-range missiles repeatedly demonstrate overwhelming advantages, procurement decisions shift. Countries want compatible aircraft, compatible missiles, compatible data links, compatible command systems. And once those countries begin building around the same architecture, the network effect expands beyond the United States. That matters strategically. A weapon sale is not merely a weapon sale. It can become an architecture sale. Buy the aircraft, train with the doctrine, connect the sensors, adopt compatible weapons, participate in exercises, share information. Now the military relationship becomes deeper. That is one reason advanced weapons have diplomatic consequences far beyond their technical specifications. Then comes the global effect. China is watching, Russia is watching, European air forces are watching, every major military is studying the same problem. What happens when stealth, distributed sensing, artificial intelligence, electronic warfare, uncrewed aircraft, and long-range weapons converge? The answer could redefine what a fighter aircraft even is. For most of aviation history, the fighter was the weapon. The pilot maneuvered the airplane. The airplane carried guns or missiles. The engagement centered on that platform. The future looks different. The fighter increasingly becomes a command node inside a distributed formation. It may detect for another shooter. It may launch a weapon using information supplied by another sensor. It may direct uncrewed aircraft. It may remain electronically quiet while another platform illuminates the battle space. It may carry weapons internally to preserve stealth. It may penetrate while less survivable aircraft remain outside defended airspace. The aircraft matters. But the network matters more. That is why simply buying a modern fighter does not automatically close the gap. Suppose Iran acquired a small number of substantially newer aircraft tomorrow. That would improve capability. But what would connect them? How many pilots would be fully trained? How many weapons would be available? What airborne early warning support would they receive? How resilient would their data links be? Could those links operate under intense electronic attack? How quickly could maintenance crews sustain high sortie rates? Could aircraft disperse? Could they be refueled at alternate locations? Would command centers remain connected after precision strikes? Could the aircraft receive targeting information without revealing themselves? These are architecture questions. And architecture takes years to build. This is one reason military modernization is so unforgiving. You cannot purchase 20 years of institutional experience in a single contract. Hardware arrives faster than doctrine. Doctrine can arrive faster than proficiency. And proficiency can disappear quickly if training hours, spare parts, maintenance capacity, and ammunition inventories are inadequate. The United States has its own problems here. Its advanced aircraft are expensive. Advanced missiles are expensive. Maintenance requirements are substantial. Long-range operations require enormous tanker capacity. Bases are vulnerable. Supply chains can be disrupted. Precision weapons can be consumed faster than industry replaces them. And sophisticated networks create sophisticated cyber and electronic warfare attack surfaces. This is not an invincible machine. It is a powerful machine with dependencies. That distinction matters, because Iran does not need to build an American-style air force to create problems for the United States. It needs to attack those dependencies. Tankers, bases, runways, fuel, communications, regional political access, ships, logistics. The conflict therefore extends beyond air-to-air combat. Iran's ballistic and cruise missiles become part of the air superiority equation. Its drones become part of it. Its ability to threaten regional bases becomes part of it. Its ability to force aircraft to operate from greater distances becomes part of it. Its ability to complicate tanker operations becomes part of it. This is asymmetric strategy. If you cannot defeat the fighter directly, attack what allows the fighter to remain overhead. And that is where the title of this story requires another correction. The AIM-260 does not make Iran irrelevant. It potentially makes one portion of Iran's traditional air defense strategy much harder. Iran still possesses other ways to impose costs. This matters because a country under air attack does not need to win control of the sky to remain dangerous. It can retaliate elsewhere. It can launch missiles. It can use drones. It can threaten shipping. It can target bases. It can attempt cyber operations. It can exploit political pressure. It can force the attacker to defend a much larger regional footprint. So American air superiority does not automatically equal strategic victory. Those are different things. The United States learned versions of that lesson in multiple conflicts. Dominating an opponent's conventional military is one problem. Converting military dominance into a durable political outcome is another. You can destroy aircraft. You cannot destroy geography. You can suppress radar. You cannot eliminate every mobile launcher. You can achieve air superiority. You cannot guarantee that every political consequence will move in your favor. That distinction becomes especially important in Iran. Iran is not a small battlefield. It has a large population, difficult terrain, extensive infrastructure, hardened facilities, dispersed military assets, and decades of experience thinking about how to survive attacks from stronger conventional militaries. A campaign that looks straightforward on an aircraft comparison chart can become extraordinarily complicated when the objective expands. Destroying a fighter on a runway is relatively easy compared with changing a government's strategic behavior. And the more ambitious the political objective becomes, the less useful a simple technology comparison becomes. This is the same underlying problem we've returned to in previous analyses of air superiority and regional escalation. Tactical dominance and strategic success are not synonyms. A military can win the opening exchange and still face a much harder problem afterward. Now, let's talk about the psychological dimension. Pilots understand threat envelopes. They train around them. They study adversary weapons. They learn what radar indications mean. They rehearse defensive reactions until those reactions become instinctive. When a new weapon expands the distance at which an engagement can become lethal, every pilot has to mentally redraw the map. Airspace that once felt relatively safe becomes uncertain. A patrol line that once seemed conservative may now be exposed. A radar contact that once appeared too distant to matter may suddenly require attention. That changes workload, and workload matters enormously in combat. A pilot has limited attention. The more time spent interpreting warnings, checking fuel, monitoring defensive systems, coordinating with controllers, and evaluating distant threats, the less attention remains for offensive decision-making. This is one of the invisible advantages of superior situational awareness. It does not simply tell your pilot more. It can force the enemy pilot to think about more. The difference compounds under stress. An F-35 pilot receiving fused information may see a comparatively organized tactical picture. An opponent receiving fragmented information from radar, voice communications, onboard sensors, and warning receivers may have to assemble that picture mentally. Even if both sides technically possess the same raw information, they may not possess the same understanding. Information is not situational awareness. Processed information is. And situational awareness is not merely a convenience. It determines decisions. Now, add time pressure. At long range, seconds matter. A pilot sees a threat. The pilot must classify it. Decide whether to engage. Select a weapon. Confirm parameters, launch, then reassess. If one system shortens that process by even a modest amount, the aircraft can begin the engagement earlier. Earlier launch means more distance. More distance means more options. More options mean greater survivability. Again, the advantage cascades. This is where the AIM-2's 6 C's significance becomes broader than its physical performance. The United States is trying to create weapons appropriate for a battle space in which targets are increasingly difficult to approach. That requirement is not primarily about Iran. It is driven by high-end competition. But capabilities designed for the hardest potential adversaries can create enormous overmatch against less modern forces. That is a recurring pattern in military history. Build a system to penetrate the strongest defense you expect to encounter. Then deploy that system against a weaker architecture. The result can look disproportionate. Iran's fighter fleet therefore faces technology developed under pressure from threats beyond Iran itself. That is an uncomfortable strategic reality for Tehran. The competition shaping American weapons is global. Iran must deal with the consequences regionally. But here's the counterpoint. The United States also cannot assume technological superiority remains permanent. Every capability creates a response. Long-range missiles encourage longer-range missiles. Stealth encourages new radar architectures. Sensor fusion encourages electronic attack against networks. Data links encourage jamming. Centralized command encourages decapitation strategies. Distributed command encourages cyber penetration and deception. Autonomous systems encourage counter-autonomy systems. The cycle never stops. AIM-260 is not the end of air warfare. It is another move in a contest. Potential adversaries will study it. They will attempt to estimate its envelope. They will develop tactics to exhaust it. They will use decoys. They will improve electronic countermeasures. They will try to target the aircraft carrying it. They will attempt to destroy missiles on the ground. They will attack logistics. They will seek longer-range weapons of their own. This is how military technology evolves. Advantage, countermeasure, adaptation, new advantage. Nothing remains revolutionary forever. The question is how large the temporary advantage becomes and whether it exists during the moment when it is actually needed. For Iran, that timing problem is serious. Modernizing an air force is expensive. Building advanced aircraft domestically is extraordinarily difficult. Importing them creates foreign dependencies. Training takes years. Infrastructure modernization takes years. Weapons integration takes years. And while that process unfolds, the other side continues moving. This creates what might be called a modernization treadmill. You're not racing toward a fixed finish line. You are chasing an opponent who is also running. If your modernization cycle takes 10 years and your opponent introduces another generation of sensors, weapons, software, and networking during those same 10 years, the gap may remain or widen. That is the strategic danger. The last generation's solution arrives against the next generation's problem. And suddenly, billions of dollars have purchased an aircraft that is modern compared with what you had, but still disadvantaged against what you expect to fight. This is not uniquely Iranian. Many countries face it. Advanced air power is brutally expensive because the ecosystem is expensive. Aircraft are only the visible portion. Training ranges, simulators, weapon stocks, maintenance infrastructure, software, secure networks, intelligence, tankers, surveillance aircraft, hardened bases, dispersal sites, fuel reserves, repair crews, electronic warfare. All of it costs money, and all of it has to work simultaneously. This is why American air power can appear overwhelming when viewed from outside. It is not one technological miracle. It is decades of accumulated infrastructure. That infrastructure creates options, and options are the real currency of military power. If one radar fails, another sensor may contribute. If one base is threatened, aircraft may reposition. If one aircraft cannot engage, another shooter may be available. If one route is defended, standoff weapons may attack from another direction. Redundancy creates resilience. Iran's challenge is that a smaller and older fighter force generally has less redundancy to sacrifice. Lose one modern aircraft from a fleet of hundreds, and the operational impact may be manageable. Lose one from a very small advanced fleet, and the percentage effect is larger. That changes commander behavior. Scarcity encourages preservation. Preservation reduces willingness to take risk. Reduced risk can surrender initiative, and once initiative is surrendered, the technologically superior force gains even more freedom to dictate the engagement. The loop closes, but there's another side to scarcity. It can encourage unconventional tactics. Iran does not necessarily have to use fighters the way America expects. Aircraft could remain hidden until specific windows. They could coordinate with ground defenses. They could exploit terrain. They could attempt ambushes. They could prioritize vulnerable support aircraft rather than stealth fighters. They could use decoys to generate false tracks. They could exploit civilian traffic patterns or electronic clutter, subject to the laws of armed conflict and operational constraints. They could attempt to create moments of uncertainty rather than sustained air superiority. That is the rational response of the weaker side. Don't fight the opponent's preferred battle. Create a different one. This is why the most dangerous assumption in military analysis is that the enemy will cooperate with your doctrine. Iranian planners understand the imbalance. They have had decades to think about it. They know an F-14 cannot simply be treated as equivalent to a fifth-generation fighter because both are called fighters. They know their greatest advantages lie elsewhere. Missiles, drones, geography, dispersal, hardened infrastructure, strategic depth, the ability to threaten regional targets, and potentially the willingness to absorb punishment while continuing to operate. Those factors cannot be measured by radar range alone. Now, I want to be honest with you about something. Discussions about military technology can become detached from what the technology actually does. We talk about engagement envelopes, sensor fusion, probability of kill, radar cross-sections, missile energy, sortie generation. They are necessary concepts, but behind every symbol on a tactical display is a human being. Inside the Iranian fighter is a pilot. Inside the American fighter is a pilot. At the airbase are mechanics. At the radar station are operators. Near strategic facilities are civilians. And once missiles begin moving in both directions, the consequences stop being theoretical very quickly. A technological advantage can make an operation more precise. It can improve survivability. It can reduce the number of aircraft required for certain missions. It can allow commanders to strike from farther away. But precision does not turn war into something clean. Every escalation creates uncertainty. Every strike creates the possibility of retaliation. Every retaliation creates pressure for another response. And every decision is being made by human beings operating with incomplete information. That matters especially when we use words like obsolete. An aircraft may be technologically outmatched without the person flying it being irrelevant. Pilots adapt. Commanders improvise. Systems fail in unexpected ways. Weather changes plans. Intelligence turns out to be wrong. A weapon misses. A supposedly destroyed radar turns back on. A unit that analysts considered ineffective performs better than expected. Another unit collapses unexpectedly. War humiliates certainty. That is why the responsible conclusion is not that a new American missile guarantees victory. It doesn't. The stronger conclusion is that the combination of American stealth, sensor fusion, networking, electronic warfare, and increasingly capable long-range air-to-air weapons can impose a set of problems that Iran's existing fighter architecture may find extremely difficult to solve simultaneously. That is already significant enough. We do not need to exaggerate it. And there is an ethical dimension here too. Deterrence depends partly on convincing an opponent that fighting would be too costly. If advanced technology creates such a strong perception of overmatch that a confrontation never occurs, then the weapon may achieve its greatest strategic effect without being fired. But overwhelming military advantage can also create temptation. If leaders begin believing that technology has removed risk, military options can appear easier than they actually are. History repeatedly warns against that assumption. The opening campaign can be spectacularly successful, while the political aftermath becomes far more difficult. Air superiority can solve an air superiority problem. It cannot automatically solve a regional political problem. Understanding why America's technological advantage may be enormous does not require pretending Iran has no capacity to retaliate or adapt. Both things are true at once. Now return to that Iranian pilot. The warning comes, the aircraft launches, the pilot climbs. A controller provides an initial picture. Perhaps the radar shows nothing obvious. Perhaps warning systems detect emissions somewhere else. Perhaps the pilot knows American aircraft are operating in the region, but cannot determine exactly where the most dangerous shooter is. That uncertainty is the battlefield. The threat is not merely the missile hanging under an American wing. The threat is the possibility that the engagement has already begun. A distant F-35 may be collecting information. Another platform may be contributing a track. An electronic warfare aircraft may be complicating the picture. A command node may be correlating information. And somewhere inside that architecture, a firing decision may be approaching. This is the real meaning of technological overmatch. The weaker side is forced to solve multiple problems simultaneously. Find the stealth aircraft, understand the network, survive the missile, protect the base, preserve fuel, maintain communications, keep the radar alive, prevent the command structure from collapsing, and somehow create an offensive opportunity of your own. One failure may be manageable. Several failures occurring together can unravel the entire defense. That is why the future of air warfare increasingly belongs to systems rather than individual platforms, and it is also why the AIM-260 should not be viewed in isolation. Put the missile on an aircraft without sophisticated sensing and networking, and it is still a potentially formidable weapon. Put that same missile inside a network that can detect targets at distance, share information, reduce the shooter's signature, coordinate multiple aircraft, and update the tactical picture rapidly, and its strategic value changes. The weapon becomes the final link in a much longer chain. Iran's problem is that attacking the final link may not be enough. It has to disrupt the chain. That means electronic warfare becomes essential. Cyber defense becomes essential, mobile radar becomes essential, passive detection becomes essential, decoys become essential, dispersed operations become essential, hardened infrastructure becomes essential, and fighter modernization becomes only one component of the response. This is where Tehran faces a resource problem. Every dollar spent modernizing one part of the system cannot be spent elsewhere. More fighters, more surface-to-air missiles, more ballistic missiles, more drones, more hardened facilities, more naval weapons, more electronic warfare, more cyber capability. Every military budget is a collection of choices. For a country expecting to face a much wealthier opponent, asymmetric systems can offer more deterrence per dollar than attempting to mirror the opponent's force structure. That helps explain why Iran has invested so heavily in missiles and drones rather than trying to build an air force resembling America's. It is rational. But rational does not mean painless. The trade-off is that Iran may be accepting substantial vulnerability in conventional air-to-air combat in exchange for greater ability to retaliate through other means. That changes what air superiority means strategically. The United States could dominate fighter engagements while still facing missile attacks against regional infrastructure. Iran could lose control of portions of its airspace while continuing to impose costs elsewhere. Both sides could claim success using completely different metrics. This is why the strategic layer is harder than the tactical one. At the tactical level, the question may be straightforward. Can an Iranian fighter survive against a stealth aircraft supported by superior sensing and a next-generation long-range missile? In many plausible scenarios, that would be an extraordinarily difficult fight. At the strategic level, the question becomes, what does winning that fight accomplish? If the objective is protecting strike aircraft during a limited operation, air superiority may be enough. If the objective is permanently eliminating every Iranian strategic capability, the problem becomes far larger. If the objective is changing Iranian political behavior, larger still. Military technology becomes less decisive as the objective expands beyond what military technology can directly control. That principle is easy to forget when a new weapon appears. Every generation has its revolutionary system, the radar-guided missile, the precision-guided bomb, stealth, drones, hypersonics, artificial intelligence. Each changes warfare. None abolishes strategy. AIM-260 belongs in that tradition. Its importance lies not in creating some magical radius in which every enemy aircraft instantly dies. Its importance lies in extending the distance at which American fighters can potentially impose risk, while integrating that risk into a sensor architecture already designed to see more, share more, and decide faster. That is the advantage. Distance plus information. Information plus stealth. Stealth plus weapons. Weapons plus training. Training plus logistics. Logistics plus doctrine. Remove one, and the system weakens. Combine them, and the effect becomes massive. Now imagine this architecture evolving another 5 years. Collaborative combat aircraft enter service in larger numbers. Uncrewed systems operate alongside manned fighters. One platform carries sensors. Another carries weapons. Another jams. Another acts as a decoy. The human pilot manages the formation rather than individually performing every task. Target information moves across the network. Weapons are assigned dynamically. Suddenly, the Iranian fighter is no longer asking, "Where's the F-35?" That may be the wrong question entirely. Which aircraft is the sensor? Which one is the shooter? Which contact is a decoy? Which platform is jamming? Which weapon is already inbound? Where's the command node? The battle space becomes distributed. That creates another problem for traditional air defense architectures. They are often optimized around identifiable objects: aircraft, radars, missile batteries, command centers. Distributed warfare deliberately blurs those relationships. The sensor does not have to be the shooter. The shooter does not have to be the commander. The commander does not have to be nearby. And the platform you destroy may not be the platform that mattered most. This is where America's technology advantage could become even more difficult to counter. Not because every individual American system is unbeatable, because destroying one node may not destroy the function. That is resilience through distribution. Iran will adapt. It has no alternative. Expect greater emphasis on passive sensors. Expect greater emphasis on drones. Expect investment in electronic warfare. Expect attempts to improve data links. Expect more hardened and dispersed infrastructure. Expect longer-range weapons designed to threaten support aircraft. Expect tactics aimed at forcing expensive American missiles to be fired against cheaper targets. That last point is especially important. Advanced missiles are not infinite. If a defender can force an attacker to spend million-dollar weapons repeatedly against drones, decoys, or low-value aircraft, economics becomes part of the engagement. A missile can be tactically excellent and strategically scarce. Magazine depth matters. Production matters. Replacement rates matter. Industrial capacity matters. The first week of a war is fought with stockpiles. The 6th month is increasingly fought with factories. That lesson has become impossible to ignore in modern conflicts. So while a next-generation missile may create overwhelming local advantage, commanders still have to decide when the target is worth the shot. This creates another layer of combat, not just kill probability, inventory management. How many missiles remain? Where are they stored? How quickly can they be moved? How many can each aircraft carry while preserving stealth? How quickly can aircraft be rearmed? How many replacements are arriving from industry? These are mundane questions. They are also the questions wars eventually revolve around. Iran's strategy would almost certainly attempt to exploit that reality. Survive the opening blow. Disperse. Force repeated sorties. Generate targets. Make the attacker spend weapons. Threaten bases. Extend the campaign. Increase political cost. That does not solve the fighter mismatch. It tries to make the fighter mismatch less strategically relevant. And that may be Iran's most realistic path. Because trying to meet America's strongest capability directly is exactly the battle Tehran would want to avoid. Here's where we stand. A fighter launches into darkness. Its pilot may be hundreds of miles from the aircraft threatening it. There may be no dramatic visual dogfight, no two pilots staring across a turning circle, no warning that looks anything like the air combat of the movies. Instead, the engagement may begin as information. A sensor detects, a network correlates, a pilot receives the picture, a weapon is assigned, and the target is forced to react. That is the shift. The AIM-260 matters because it extends the reach of that architecture. The F-35 matters because stealth and sensor fusion can improve the conditions under which that weapon is employed. American support systems matter because they expand the information picture. Electronic warfare matters because it can degrade the opponent's picture. Training matters because pilots must turn information into decisions. Logistics matters because none of it works for long without fuel, maintenance, weapons, bases, and spare parts. This is not one weapon replacing an entire air force. It is one new weapon entering an ecosystem that may already possess decisive advantages over much of Iran's fighter architecture. And that is potentially more consequential. Iran's aircraft do not have to be destroyed to become operationally marginalized. If they cannot reach useful firing positions, they cannot reliably protect the targets assigned to them. If they are forced defensive every time they approach, they lose initiative. If their bases are under pressure, sortie generation falls. If ground radars are degraded, situational awareness suffers. If communications are disrupted, coordination becomes harder. If fighters become scarce, commanders become more conservative. Each effect feeds the next. Cascading. That is the word to remember. But the opposite warning matters just as much. American technological superiority does not make war predictable. Iran can retaliate asymmetrically. Missiles can threaten bases, drones can consume defensive resources, geography can hide systems, decoys can waste weapons, electronic warfare can create uncertainty. Support aircraft can be pressured. Political constraints can limit operations. And even the most sophisticated aircraft remains a machine operated by humans in an environment where mistakes have consequences. So, has one American weapon literally made Iran's entire air force obsolete? No, that is too simplistic. But has the combination of next-generation American air-to-air weapons, fifth-generation aircraft, fused sensors, networking, electronic warfare, and mature operational doctrine created an environment in which much of Iran's existing fighter force could struggle to perform its traditional defensive mission against a full-strength American air campaign? That is a much stronger argument. And the evidence points toward a profound imbalance. The difference matters. One claim is hype, the other is military analysis. The most important question now is not whether Iran can buy a newer fighter. It is whether Iran can modernize the entire chain quickly enough. Detection, tracking, command, networking, electronic warfare, weapons, training, maintenance, dispersal, survivability. Because America's advantage is increasingly concentrated not in any one airplane or missile, but in the connections between them. Break those connections, and the fight changes. Fail to break them, and an Iranian pilot may discover the central problem of 21st century air combat. The aircraft he needs to defeat may never need to come close enough to give him a fair fight. The dogfight is not disappearing completely, but the goal of America's newest air combat technology is increasingly to make sure the dogfight never begins. See first, understand first, shoot first, force the opponent defensive, then let distance do the rest. That is the real story behind the AM-260, and that is why this weapon matters far beyond its classified range figure. If this breakdown gave you the strategic context you simply cannot get from a 30-second headline clip, share it right now with someone trying to actually understand what's happening. And here's the question I want you to think about. If Iran knows it cannot realistically match America's entire air combat ecosystem aircraft for aircraft, where should Tehran invest its limited resources? Newer fighters, longer-range ground defenses, electronic warfare, drones, and missiles, or an entirely different asymmetric strategy? Drop your take below. I read every comment. And hit like if this analysis delivered real value. Because the next stage of this story may be even more important than the missile itself. The real transformation begins when America's long-range weapons are no longer tied primarily to individual fighters, but become part of a distributed network of stealth aircraft, autonomous systems, electronic warfare platforms, and remote sensors operating as one combat formation. When that happens, the question will no longer be whether an older fighter can defeat a newer fighter. The question will be whether an older air defense architecture can survive a battle space in which it may never know which platform actually started the engagement. And that is the development we'll be watching next.